Hello everyone. So this is Yaman and today we are going to study Sieve of Eratosthenes and we are going to study how is it implemented, why is it implemented and what is its actual implementation. So let us start. Just one second. Okay. So this person is Eratosthenes, although this is a cartoon. Yeah, but he's Eratosthenes. So let us study what is a sieve of Eratosthenes. As you know that this is a sieve, and pretty much we are going to um, study about this sieve. What does this sieve does? This is a sieve to find prime numbers, and so before starting, we must know what are prime numbers. Prime numbers are natural numbers. They have exactly two distinct divisors, and the two distinct divisors are 1 and the number itself. Thus, the prime numbers are natural numbers. They have exactly two distinct divisors, and the distinct divisors are 1 and the number itself. What are natural numbers? Natural numbers are any number that is greater than equal to 1. Okay, so this is a small list of initial prime numbers, and as you can see that the list begins from 2 and not from 1. Why 1 is not there in this list? uh, 1 is not there in the list because 1 does not have two distinct divisor. Although 1 is the number itself, but 1 does not have any other divisor. That is why 1 is not a prime number, and thus our the smallest prime number is 2, and the list goes on. Okay, so these are prime numbers. So this is time for some visuals, and we're going to exactly see how Sieve of Eratosthenes works. See, we first start from 2. We mark all the multiples of 2 as not containing any primes. Thus 2, 4, 6, 8, 10, 12 and so on were marked. Okay, then we start from 3. Let me start it again. Then we start from this. Then we start from 3. We mark all the multiples of 3 as non-prime. 3, 6 has already been marked. Then we mark for 9, then for 12, then 15, then 18 and so on. Then the first unmarked number is 5, and we mark all the numbers that are multiples of 5. For example, 15, 25, 20 and so on. So let me concretize it. See, this is a small example. We create a list of all numbers from 2 to 50. Currently all of these numbers are unmarked. Okay, the first and the smallest unmarked number is 2, so we begin by 2. We mark, that is cross, all the multiples of 2. The first multiple of 2 is 4, so we cross it. Then 6, then 8, then 10 and so on till 50. Then the next smallest unmarked number is 3, so we mark all the multiples of 3 as non-prime. The smallest multiple of 3 is 6. 6 has already been marked, so we leave it. Then 9. Then 12 has already been marked. Then 15, 18 and so on. Okay, so this has been done already. So we have already marked all the multiples of 2 as well as 3. Okay, so this is the complete list. Then the smallest unmarked number is 5 and not 4. See, 4 has already been marked. So we mark all the multiples of 5 now. As you can see that the smallest multiple of 5 is 10, which has already been marked. Then 15, which has already been marked. Then 20, it has also been marked. Then 25, which has not been marked, so we'll mark it here. Okay, it is marked, and as you can see that this has been marked here. Then 30, then 35, then 40 and so on. Okay, and we continue this process. What's the process? We take the smallest number which is unmarked, we mark all the multiples of that number. For example, the smallest number was 2. We marked all the multiples of 2 as non-prime. Okay. Then uh, after marking all the multiples of 2, we search for the next smallest number which has not been marked, and in this case it was 3. So we mark all the multiples of 3 as non-prime, and thus we marked 9, 12, 15, 18 and so on. Then we take the next smallest number which is not been marked, and we uh, mark all its multiple as not prime, and we continue this process till no number is left which has not been marked. Okay, and the numbers which have not been marked are prime numbers. So let me concretize the algorithm. This is the algorithm. We create a list of consecutive integers from 2 through n. Let the first number be equal to 2, since 2 will always be unmarked first, the smallest prime number. We enumerate the multiples of p, that is, the first number is 2, p. We start from p and we go to n in its multiples. The first number would be 2p, then 3p, then 4p, then 5p, and so on till n, till k into p is less than n. Okay, till this condition is not satisfied, we mark all the multiples of p as non-prime. Then we find the first number greater than p in the list that is not marked, and we continue the same process. That is, we enumerate the multiples of p by counting to n, and we unmark those multiples. And how long do we continue this process? Until no number is left. When there is no number left, we just say that we have completed the algorithm, and all those numbers which are left unmarked after completing this whole algorithm are prime numbers. So this is the C algorithm. As you can see that we have taken a bool array of prime numbers of all numbers. The size of the array is n plus 1. The problem is to find all the prime numbers till n. Thus we have taken an array of size n plus 1, and it is of type bool. That is, it will contain either 0 or 1. Initially we set all the all the numbers as prime. Okay, so this is similar to our unmarking scenario. Currently we have unmarked all of them. Then we choose the first unmarked number, which will invariably be 2, and so we see that if the prime is p is true, that is, it is unmarked, we this condition evaluates that the number is unmarked. Then we continue in the loop and we mark it, and we mark all the multiples of the number p. And how long this process continue? This process continues until p is less than square root of n. This is a small optimization. Square root of n. So this condition is equivalent to this. And after this loop completes, we just print all the numbers which are unmarked, which are unmarked, and those numbers are prime numbers. So I think you'll understand. You must have understood the process of evaluation of prime numbers, and my references, as you must have evaluated, that these were the references: Wikipedia article, the Geek Studies website. Thank you.